All right, let's dive into something really cool, one of the most beautiful ideas in all of math. We're going to look at the secret DNA that's hidden inside every single number. Ready? Let's do this.
When you think about numbers, all of them, going on forever, does it just seem like a big random mess? Or is there something else going on, like a hidden structure, a secret code that ties them all together? Well, I'm here to tell you, the answer is a big yes. There is a code, and honestly, it's way more beautiful than you'd think. All right, so to crack this code, we gotta meet the main characters. These are the absolute basic building blocks of the number universe. Think of them like atoms or Lego bricks. We're talking about prime numbers. So, what exactly is a prime number? Well, it's pretty simple. It's any whole number bigger than 1 that you can only divide by itself and, well, 1. Numbers like 2, 3, 7, 11, 23. You try to break them down into smaller whole number pieces and you just can't. They're the fundamental, indivisible elements. Okay, so if these primes are our Lego bricks, the obvious next question is, what can we actually build with them, right? What happens when we start snapping them together? This is where things get really, really interesting. So let's play the role of creator for a minute. We're going to take these prime building blocks and see what happens when we make bigger, more complex numbers. We call these composite numbers, just by multiplying them. And you know what? The process is super simple. Step 1, you just choose your primes. Step 2, you multiply them together. And step 3, boom, you've just created a totally new composite number. It's that easy. Check this out. This is what's so cool. We take just a few primes, 7, 11, and 23, multiply them, and we get 1,771. Okay, simple enough. But now watch this. Let's just toss a 3 into that mix. Suddenly, we're at 5,313. And if we throw in a 2, bam, we're over 10,000. Use that 2 one more time, and we've doubled it again to over 21,000. See? The same basic ingredients can create this huge variety of numbers. And here's where it gets kind of mind-blowing. It's been proven that there are infinitely many prime numbers. I mean, they just keep going forever. So what does that mean? It means our supply of these building blocks, it never, ever runs out. We can literally build forever. Okay, so building numbers up from primes, we got that. It's like building with Legos. But can we go the other way? Can we take some big, messy-looking number and reverse engineer it? Break it down to find the exact prime ingredients it was made from? All right, let's put that idea to the test. Here's our number, 32,760. Yeah, it looks kind of big and intimidating, right? So let's imagine this is our crime scene. We're the detectives, and our job is to find the hidden evidence, the DNA, buried inside this thing. And our main tool for this investigation is going to be something called a factor tree. The strategy is pretty straightforward. We're just going to keep breaking this number into smaller and smaller pieces, just chipping away at it until we can't go any further, until all we have left are our prime suspects. Okay, first break in the case, and it's an easy one. The number ends in 0, so right away, we know we can split it into 10 and 3,276. Now, neither of those are prime, so they're not the final answer. We've got more digging to do. And here we go. That 10 breaks down immediately into 2 times 5. Yes, those are both primes. That's our first bit of hard evidence. And the 3,276, we can pull a 2 out of that, leaving us with 1,638. See, we're making real progress here, pulling out these primes one by one. And we just keep going. We take that 1,638 and we break it down, and then we break down its pieces, and so on and so on. We're just following this trail all the way to the end until every single path stops at a prime number, one of those fundamental pieces that just can't be broken down anymore. And after all that work, this is it. This is what we find. The prime factorization of 32,760. It's made of 3 2s, 2 3s, a 5, a 7, and a 13. That's it. This beautiful little formula, that's the secret recipe for our big, complicated number. So, this journey we've been on, building numbers up and then tearing them back down, it all leads us to one of the most important rules in all of mathematics. It's time for the big reveal. So let's just recap. We've seen it's like a two-way street, right? On one side, we can multiply primes together to build bigger numbers, and on the other, we can take any of those bigger numbers and break it all the way back down into its prime parts. These two ideas working together, that's where the magic happens. And here it is, the fundamental theorem of arithmetic. It says that every composite number can be broken down into a product of primes. But here's the kicker, there is only one way to do it. That's the part that changes everything. It's totally unique.
Think about what that means. That list of primes we found for 32,760, that wasn't just a possible recipe. It is the only recipe. There's no other combination of primes in the entire universe that will multiply together to give you that exact number. It's like a fingerprint, a unique, unforgeable identity for that number.
So, okay, why does this matter? Why is this one little rule so incredibly important? Let's zoom out and see the big picture. Well, this theorem, it's the answer to that question we started with. It shows us that the universe of numbers isn't just some chaotic mess. Underneath all that complexity, there's this perfect, predictable order. Every single number has its own unique place, defined by its prime DNA. And that's exactly why we call it fundamental. Its basic, crucial importance is all about that guarantee of uniqueness. I mean, this single idea is the foundation for huge parts of math, and even stuff like modern computer encryption. The fact that every number has one and only one secret code, well, that's a cornerstone of how we understand the world. So think about it. The incredible, infinite complexity of our number system, it all comes from a few really simple, unbreakable rules. It really makes you wonder, doesn't it? What other simple rules like this are out there? Quietly building all the complex beauty we see everywhere, in nature, in art, in the entire universe.